We mentioned something about the spherical equivalent. So we said that the spherical equivalent is the dioptric mid-value of the conoid of Sturm. So this will be equivalent to the circle of least confusion, meaning that if I have this is a patient who have astigmatism, and this patient have a first focal line and a secondary focal line, and this whole retina has an image, and this image is blurred, very blurred, because this patient have a conoid of Sturm. So what happens if I put a patient in front of this patient a spherical lens? This spherical lens equals the spherical equivalent. So if I put a spherical lens in front of the patient's eye, this spherical lens equals to the spherical equivalent. This will lead to movement of the circle of least confusion over the retina. So this will lead to a better vision. The vision will be better, but it will not be the best, because this is again a circle of least confusion. It is not a single point. So the value of the spherical equivalent is that it will convert the cylindrical value into a spherical value, or to the most close spherical value that the patient can wear, and make him much more comfortable. But if we need to have the best vision, then we need to put the patient a toric lens. A toric lens meaning that it is a spherocylindrical lens, and this lens will now move the circle of least confusion into the retina and make it into a single point, leading to the best vision. What will be the uses of the spherical equivalent? This can be used for the contact lenses. So usually the contact lenses are calculated based on the spherical equivalent. So for example, if a patient has a sphere -6 and he has cylinder -4, then the patient will wear, or the optician will give him a contact lens of -8. So this will be like a sphere plus half of the cylinder value. So it will give the maximum vision that can be perceived from a spherical lens or spherical contact lens. Cylinder also is a device that is used for refraction. It's used for the subjective refraction. We will postpone it to the instruments, or sorry, to the refraction lecture. So it will be the right place to discuss the principle of this, but you can know from now that is based on the spherical equivalent. So how can we calculate the spherical equivalent? This is also one of the common questions in the exam. The spherical equivalent can be calculated by knowing the dioptric power of each meridian. So for example, if we have a meridian here and meridian here, this meridian has a power of 8 diopter, -8 diopter, and this meridian has a power of +3 diopters. So the spherical equivalent will be the summation of these two meridians, or these two powers. So it will be -5 divided by 2. So this patient will should wear a -2.5 spherical glasses. Or it is the most common equation that we use in practice and also asked in the exam is the spherical equivalent. So the spherical equivalent, or the equation, is the sphere plus minus half of the cylinder. So sphere plus half of the cylinder will give rise to the spherical equivalent that can be used as a contact lens or can be used in glasses, but it will not give the best vision, as we said. We have mentioned something about transposition in the early lectures, so we just will go through more details about transposition now. So what is transposition? Transposition is changing the lens form from one form to another. So we have two types. Simple transposition is what is used for the glasses, and the toric transposition is what is used for the toric contact lenses. So how can we change the position of the cylinder? In case of simple transposition, we can change the sphere to meniscus form. So the meniscus form of the glasses is the best form of the lens. So if we want to make we usually, or the glasses are not made by just making a spherical anterior surface and spherical posterior surface, or convex anterior surface and convex posterior surface for the plus lens, and the concave anterior surface and the concave posterior surface for the minus lens, because this form will cause more large aberrations. We will say about aberrations maybe in the next week. But rather than this, we will make a simple transposition by doing a meniscus form. So a meniscus form meaning that the lens has convex surface and the concave surface according to the refracting power that we need. So if we need a plus power, then we will make the convex surface more powerful than the concave surface. If we need the lens, the total power to be of concave or of minus value, so we will make the concave more than the convex. So this is what's called simple transposition of the form of the lens. Another simple transposition, or what's more important, is the transposition of the cylinder to increase or to decrease the weight of cylinder and to make this or to change the cylinder sign. For example, if we do a refraction for one patient and you find that the cylinder of one eye is in plus value and the cylinder of the other eye is minus value, in such a condition, the patient will not tolerate that there are different cylinders in both eyes. So either to put them both in plus value or both in the minus value. So to do this, we do what's called transposition. So how can this be done? We have mentioned this before. Let's say for example, if we have a patient who have a spherocylindrical lens. So this patient, meaning that meaning that he has a spherical lens or a spherical error. So he has +3 spherical error. +3 spherical error meaning that the +3 is present in all meridians. Cylindrical meaning that he has a cylindrical error as well, and by meaning cylinder, meaning that they have a refracting power of one meridian only. So they will have -3, for example, at this example, they have -3 error at the vertical meridian, while other meridians are normal. So when we are combining both of them, this can be mentioned as +3 sphere, -3 cylinder, axis 90, so this +3 sphere, and this -3 at axis 90. So this is one notation of this lens formula. Also, if we do algebraic summation of the power of the vertical and the horizontal meridian, so if we equal +3 plus -3, it will be 0. So the net power at the vertical meridian will be 0. And if we summate +3 of the horizontal meridian here to 0 in the horizontal meridian there, it will be equal +0. So this lens formula will be equal to a lens that has only +3 at axis 180 degrees. So this is what's called transposition. So we change it here. Instead of giving the patient a heavy glasses that has a +3 lens and -3 in the axis 90, we changed it to a simple form of only +3 with at the axis of 180 degrees, and he will see the same thing. So both of them will be the same. Also, if we want to change the minus form of the cylinder to plus form, and this will be the main reason we do transposition. So we change the minus form to the plus form, or we change the plus form to the minus form in order to make the two eyes have the same cylindrical sign. So how can we do it mathematically? There are simple 3 rules to have to make a simple transposition. First, add the sphere to the cylinder, and the resultant number will be the new sphere. Then change the sign of the cylinder to make the new cylinder, and then the axis of or the new axis will be the perpendicular axis. And how can we obtain the perpendicular axis? If the axis or the old axis is less than 90, then add 90. If the old axis is more than 90, then subtract 90. Let's have an example. If we have a patient who have +1 -3 axis 70, and we want to do simple transposition of this formula, and this is one of the almost always present in the exam of optics. So you will face a case of transposition to make it in the exam. So this is unavoidable. So how can we obtain simple transposition of this formula? So we will summate the +1 plus -3. This is algebraic summation. So that the total will be -2. This will be the new sphere. Then the -3 will be the new cylinder, but will change the sign. So -3 will be +3. And the axis will be the perpendicular axis. So the 70, what will be the perpendicular axis to 70? Since the 70 is less than 90, so we will add 90. So 90 plus 70 will be 160. So here we did simple transposition. So this should be go on both ways. So if we would change this form to this form to know that they are both similar, if we want to do simple transposition for this formula, so the new sphere will be addition of the old sphere to the old cylinder. So -3 and the +3 will equal +1. Change the sign of the cylinder, so +3 will be -3. The perpendicular axis to 160 will be 70. I hope that this is clear. Another form, or the second form of transposition, it is called the toric transposition. Toric transposition is used for transposition of the toric contact lens. So the toric contact lens have another variable or another figure which is called the base curve. The base curve is that we will talk about it when we will discuss the contact lens lecture. So just to know it by a figure, like a number now. So we have a sphere, or the toric formula, meaning that it is the sphere divided by a base curve over the cylinder. So how to calculate the toric formula? So if the cylinder and the base curve signs are different, first we do need to do simple transposition. This is usually one of the common mistakes while addressing this question in the exam. You find that the base curve and the cylindrical signs are different, and you forget to do simple transposition. So again, if they are different, do simple transposition, and then the new sphere will be the sphere minus the base curve, and the new cylinder will be the cylinder plus base curve in the axis of the cylinder. The new base curve will be the base curve in the base curve in the cylindrical axis plus 90. So let's now see how to calculate the toric lens formula. For example, if we say in the exam, you have now a contact lens or a toric lens that has a sphere of +7, has a cylindrical power of -3 in the axis 120, and the base curve of +6. How to do a toric formula? Remember, this is the formula. Sphere divided by base curve over the cylinder. So answer, here we can find that the cylindrical sign or the cylinder sign is different from the base curve. So here is minus and here is plus. So first we need to do a simple transposition in order to make the base curve sign and the cylinder sign the same. So to make the cylinder transposition, so minus 3, we first do a simple transposition for this. So plus 7 plus minus 3, it will be plus 4. Change the sign of the minus 3, so it will be plus 3. The perpendicular axis over 120 will be 30. And the base curve of plus 6 again. So this is the formula that we will work on, not this one. So discard this one and now work on this. So what will be the new sphere? The new sphere will be the sphere minus the base curve. So the sphere here is plus 4 minus 6. So the new sphere will be minus 2. The new cylinder will be the cylinder plus the base curve in the cylindrical axis. So the cylinder here is plus 3 plus 6, so it will be plus 9 at this new cylindrical axis, which is this, will be 30. So this will be the new cylinder. The base curve will be equal, or the base curve will be the base curve, but on the perpendicular axis over the cylindrical axis. So it will be the same value of the plus 6, but with the perpendicular axis to the cylindrical axis, which will be 120. So this will be the base curve. So the toric formula is, if we started with plus 4 sphere, plus 3 axis 30, base curve plus 6, then the toric formula will be minus 2, which is the new sphere, plus 6 axis. Sorry, this is plus 6. Yes, plus 6, yes, that's right, sorry. The base curve will be plus 6 in 120 divided by plus 9 over 30, or axis 30, which is the new cylinder. So again, the sphere divided by base curve over the cylinder. This is what's called toric length formula. So this needs a lot of practice. You need to make some examples for yourself. So just make up any figures, put any numbers as a sphere and the cylinder and the axis and the base curve, and practice a lot in order to memorize these steps. How to get out the new sphere, how to get out the new cylinder, and how to get out the new base curve, because these rules will not be mentioned in the exam. To be honest with you, usually in the exams are asked the simple formula or the simple transposition, but sometimes toric formula is asked. So you should also know their rule or know how to convert the toric formula of the contact lens. Okay, so let's talk about the lens verification. What is meant by the lens verification? By lens verification, we mean that we have several methods to detect the type of the lens and the power of the lens, the optical center of the lens, and the plane of the lens. So this is more like a practical aspect of the optics. It can also be asked in the MCQ exam, but this will be more useful for your practice. If you have a lens or the lens doesn't have any figure or any number, and you want to know what is the power of this lens and what is the type of it, is it convex or it's a concave? So what are the methods that we use in order to find out? First of all, let's talk about detection of the lens type. Detection of lens type, meaning that if I give you a lens and ask you what is its type, then you should know whether it is spherical or astigmatic or it is a prism. So this can be done by studying the image formed by two crossed lines at 90 degrees when viewed through the angle. So you can place the lens like you see two crossed lines in the floor, for example, and you place the lens over them. And by moving the lens and by rotation of the lens and the detection of the behavior of these lines, you will be able to know what are or what is the type of this lens. Let's see, for example, the convex lens. So for the convex lens, if you place the convex lens from the trial lens frame over across the lines, then you move this lens in one direction, you will find out that the cross will move in the opposite direction. So it will move against the direction of movement. Not only this, but the image also is large. So the more you enlarge the power of the lens, the more you will find that the image of the cross become more large. And this is logic. So we all know that the convex lens increase the magnification or increase the size of image. So the convex lens will produce a large image and moves against the direction of lens movement. So if we move the lens like this, the image will move like this. So what is the explanation behind this? This will be explained by the basis of prismatic effect of the lens periphery that we have just mentioned in the previous lecture. So if we have a convex lens, this means that the lens is considered as a base-to-base prism. As we go to the periphery, the most powerful prism will be on the periphery, and as we go toward the center, the least refraction will be near the paracentral area, and there will be no refraction at all at the center of the visual axis. So if light ray will fall into the eye, the image and the eye will move toward the apex of the prism. So here is the base and here is the apex. So I will see the image like here. So what happens if I move the lens like this? So the same light ray will enter through the periphery of the glasses, but it will undergo much more stronger prismatic effect. So it will deviate more toward the base, leading to the image. It will deviate more toward the apex. So it will lead to deviation of the image toward the apex, so that the image will be seen moving in against direction of the direction of movement. So here is the direction of movement, and here will be the direction of seeing the image. The reverse occurs with the concave lens. So for the concave lens, if we have a concave lens like here, and we viewed cross lines, and you remove the lens of, for example, in this position, you will find that the cross will move with the same direction as your movement. Not only this, but the image all will be small. So a minus lens will cause a small image that moves with the direction of movement of the lens. And again, this can be explained by the theory of the prismatic effect of the lens periphery. So we know that the concave lens is an apex to apex prism. So this is an apex to apex prism, and as we go to the periphery, the prism become most strong, or the periphery is more thick, so it is the strongest prism. So if we have a light ray that is normally deviating toward the base, so that its image will deviate toward the apex, and we now move the lens, the same light ray will deviate toward the base, and its image will deviate toward the apex. So the image looks like it is displaced at one side, that it will be the same like displacement of the movement of the lens. So this can be done for detection of the type of a spherical lens. But in case of a cylindrical lens, there will be other maneuvers in order to detect if there is a cylindrical lens or not. For example, the spherical lens will cause no distortion of the cross. So if you move the direction at any direction, and if you rotate, then you will have no distortion at all. And the speed of movement and the amount of blurring will depend mainly on the power of the lens. And if it is a spherical error only, then the power of, or the speed of movement, will be the same in all directions of the lens. And if you have rotation of the lens, it has no effect on the image of the cross lines, as there will be no distortion, because this only occur with the cylindrical lens. So the astigmatic lens will cause distortion of the cross unless if the axis is coinciding with the cross line. So the distortion is called the scissoring effect, which will give you an idea about the astigmatism. So for what do we mean by the scissoring effect on rotation? So if you, here is the +1 here. Note, if we rotate the lens like this, you will find that the cross is rotated. So the larger the cylinder, the more the rotation. So this means that this cylinder is not spherical only, because if it is spherical only, this rotation or this scissoring will never happen. The last question in identification is how to identify that we have a prism. So if you have a lens or a lens prism, then this prism has no optical center, and it will only displace the line of the cross regardless of the position of the cross. So it will deviate the image toward the apex as the light rays will deviate toward the base. So here we have a prism, and once we put the prism over the cross, this will lead to displacement of the cross toward the apex. So here is the apex of the prism, and here is the base. So it will lead to displacement of the cross toward the apex. Again, if we want to move, we don't need to rotate. Once we place the lens in front of the center, then this will lead to displacement of the cross toward the apex. The second way to detect the lens is the detected lens power. So we now know if the lens is plus or minus. We can know that if the lens is spherical or astigmatic, or it's a prism, but we need now to know what is the lens power. So this can be done by several methods. The first one is called the neutralization of the apparent movement. So by neutralization of the apparent movement, we will see later, we have the lens clock or Geneva lens measure, the photometer or the lensimeter. Neutralization of the apparent movement is the most simple way. So if you have a lens, then you can put a combination of lenses, like putting a plus with the plus or minus with the plus, until you make a combination that you will move across the line, then you will see no movement. For example, if we have here this lens that you don't know what is its power, so you move it across along a cross, and you will find that this cross will move against the direction of your movement. So you will know that it is a plus lens. Then you will combine it with a minus lens like this, and then you rotate or you remove this combination again over the cross. If there is no movement, so this minus lens has the same power of the plus lens, but with just different sign. So it is now acting as a parallel plate of glass with no refraction. If we have an astigmatic lens, meaning that we have different meridians, then every meridian needs to be neutralized separately, but this is theoretically and usually this is not used or not performed on the real practice. Another historical method that were used to measure the power of the lens is called the Geneva lens clock. So maybe it is used for in some hospitals. I'm not aware that there are any hospital that is working with that. But let me just tell you its principle. So this Geneva lens clock has 3 pins, one which is movable and the 2 are stationary. And you put this lens clock over the surface of glasses like this. Then you have 2 scales, one by red and other in black. The one in black is the plus, and the one in red is the minus. So you may see that this lens is pointing to 3.5, or 13.5. So is it by plus or is it by minus? So this will depend mainly on the movement. Is it moving like in this direction? So it will be on the plus from 0, 1, 2, 3, 4, or the scale is moving on this direction, so it will be 0, 1, 2, 3, 4 until it reaches 13. We can also know if the lens is a spherical or cylindrical or meniscus by the Geneva lens. So how can we know that the lens is spherical? This can be done by rotation of the lens at 360 degrees. You will find out that the power is fixed or the power is constant at all meridians. However, in case of a cylindrical lens, there will be two main powers that are perpendicular to each other. There will be a highest power and the lowest power. Meniscus lens, in case of meniscus lens, we need to measure both surfaces and combine both of them. So for example, if we put a Geneva lens or the Geneva lens over the glasses, and then we can first measure the convex anterior surface, so it will give a plus value, and then we can measure the concave posterior surface, so it can give a minus value. So by algebraic summation of these values, this will lead to knowing the power of the lens. The disadvantages of the Geneva method, so we don't use it anymore, that the lens is calibrated for crown glass, which has a refractive index of 1.5. So for example, if we use another type of glass, this will lead to different calibration and different measurement. Also, it doesn't take the thickness of the lens into consideration, and we cannot measure the axis accurately. So we cannot of the cylinder, of course. So we cannot reproduce the result of cylindrical measurement, and we cannot measure the prism. And it has the accuracy should be calibrated at regular basis of time. Another method that is used, it's called lens gauge, but this is also no longer used. The main or the gold standard device for measurement of the lens power here is called the photometer or the lensimeter, either the manual or the automated. And this manual or the photometer will be discussed in the instrument lecture, because this will be the right place to cover it. Finally, detection of the optical center. So how to know where is the center or the optical center of the lens? This can be done by the lensimeter. So how can this be done? If we put the lens in the lensimeter like here, you can see clearly the center of the glasses. Also, this can be done by a crude method, which is the deviation of light of the cross. So for example, let's say that when you put this lens is a toric lens or a spherocylindrical lens that has different power in both the spherical and in both vertical and horizontal. So once you put the glasses or you put the lens, you will find that there is displacement of the mirrors or displacement of the cross inside the lens. So what will you do? You will move the lens in the vertically and horizontally in order to that the lines outside the lens will coincide with the lines inside the lens. So by doing this, you will now know what is the optical center of the lens by recording your movement. Another simple method, which is by projecting a pin torch into the glasses. So if the glasses show that there is usually it will show two images of the light torch, and by moving the glass from side to side until these two lights will coincide to a single light, so this will lead to the this will denote the presence of the central light.